A standard water sprinkler deploying over a server rack triggers a secondary emergency. Water introduces conductivity to high-voltage environments, causing catastrophic short circuits. This video is for educational purposes. All fire suppression design and interaction must follow NFPA 2001 and the guidelines of your local authority having jurisdiction. A Class C fire is defined by the energized state of the equipment. When current jumps across damaged insulation, the resulting electrical arc can exceed 35,000 degrees Fahrenheit, instantly igniting nearby materials. Technically, once power is fully disconnected, the hazard reverts to its underlying fuel, usually Class A plastics and paper or Class B flammable liquids. But in critical facilities, immediate de-energization often means crippling downtime. Fighting the fire while electricity flows requires non-conductive suppression agents to protect both the operator and the hardware. In these environments, continuous electrical energy turns traditional fire suppression into a deadly liability. Sprinklers leave behind corrosion and ruined motherboards. For zero downtime operations, saving the building is useless if the internal hardware is destroyed. This risk requires clean agents, gaseous systems that extinguish flames without leaving residue or thermal shock. Decades of operation in data hubs and historical archives have proven the necessity of these non-water alternatives for protecting high-value assets. The upfront investment in clean agents is designed to compress facility recovery time from weeks of remediation to a few hours of ventilation. The system's efficacy depends entirely on room integrity. The architectural envelope must be tight enough to contain the specific gas concentration or combustion will resume. Engineers prioritize clean agents because the secondary damage caused by water often poses a greater operational threat than the initial fire. Modern suppression is dominated by three specific agents: FM200, Novec 1230, and carbon dioxide. Engineers evaluate these based on three metrics: their chemical suppression mechanism, human safety limits, and global warming potential. FM200 is a hydrofluorocarbon that extinguishes fire by extracting heat and interrupting the chemical chain reaction. However, its global warming potential of 3,500 has triggered a mandated industry phase-down. Novec 1230 is a fluorinated keton, stored as a liquid but discharged as a heat-absorbing gas. With a GWP of just 1, it became the preferred environmentally friendly alternative to FM200. Despite its performance, the industry is facing a severe supply crisis for this specific compound. 3M is voluntarily ceasing Novec production by 2025 due to global regulations on PFAS, or forever chemicals. Carbon dioxide and inert gases use a different approach, displacing oxygen to drive ambient levels below the 15% combustion threshold. While FN200 and Novec are suitable for occupied IT rooms, high-concentration CO2 is restricted to unoccupied hazards due to its lethality. Delivering these agents requires a precise network of pressurized cylinders, fixed piping, and calculated discharge nozzles. Facility managers must balance fire efficacy, human safety, and strict environmental law. No single agent is perfect. Releasing these agents safely depends on a specific automated logic. Control panels use cross-zoned detection. The first detector triggers a local alarm and shuts down the facility HVAC to prevent gas dilution. Then a second detector on a completely different zone confirms the fire and immediately starts a 30-second pre-discharge timer. Inside the enclosure, a physical abort button provides a manual override. This button only pauses the countdown for investigation. Releasing the switch resumes the timer immediately. It does not reset the system. This delay is vital for CO2 systems. Because the gas aggressively displaces oxygen, anyone trapped inside faces immediate lethal asphyxiation. Safety codes mandate visual warnings, including placards and synchronized strobes, to alert personnel to the hazard of the agent itself. Following a discharge, door discipline is non-negotiable. Only enter with SCBA gear or clearance from the authority having jurisdiction. The system's sequential logic provides a calculated window for human evacuation. Maintaining these systems involve navigating specific regulatory frameworks. NFPA 2001 defines the standards for the design, concentration limits, and testing of clean agent systems. NFPA 72 governs the signaling code, ensuring detectors and release panels communicate reliably. OSHA 1910 Subpart L integrates these requirements into workplace law, specifically addressing asphyxiation and electrocution risks. These codes translate fluid dynamics and toxicology into binding survival protocols. For facility managers, routine maintenance requires a specific checklist. First, audit all signage. Ensure do not enter placards and strobe lights are functional and visible. Second, conduct egress drills. Staff must recognize pre-discharge alarms and know the difference between an abort button and a manual pull station. Third, verify room integrity. Check that all doors, subfloors, and ceiling tiles seal properly to prevent agent leakage. Finally, brief all contractors. External workers must not compromise the detection network during routine IT or HVAC maintenance. The system's success depends on the operator respecting the balance of its chemistry and physics. If you want to learn more about workplace safety and OSHA rules, subscribe to HSEstudy.